Whoops. So, a little bit of a review. Whoops. Little bit of review. Let's talk about equilibrium, right? We've been talking about equilibrium, but in the case where we are dissolving a compound in solution, specifically in a case where the compound that we're dissolving doesn't typically dissolve very much. It's not soluble. We could say, based on our solubility rules, right? If we look at our solubility rules and we think about a compound like lead chloride, we would say lead chloride, chloride ions are generally soluble, except for in the case of silver, lead, and mercury. Therefore, lead chloride is a solid. It's not going to dissolve. It's not going to dissolve. But we've all grown up now. We're different than we used to be. We used to think, oh, that won't dissolve. But now what do we think, Alyssa?
That it could dissolve depending on the situation.
That it can dissolve just a tiny bit, an amount. Right? It used to be there were things that were soluble and there's stuff that's insoluble, and that was the line. Just like we used to say there's strong acids and weak acids, and there's a line between them. That's what we used to think. But now we know with an equilibrium constant, we can know how strong the acid is. It's a weak acid, but it could be a little bit stronger than every other weak acid. Same thing with this K. It will tell us to what degree this dissociation will occur, right? It'll tell us to what degree this solid becoming soluble will occur. And we call that K a KSP, where SP stands for solubility product. Solubility product. Let's see. Okay. Okay. All right. So, yeah. So if the KSP value here was 1.3 times 10 to the minus 12, for example, we could know how much of our lead ion and our two chloride ions will actually result, or in other words, what molarity of this material will actually dissolve. And we call that the molar solubility, the molar solubility. Now, we know from our equilibrium discussions already what the K for this reaction will be. It will be the concentration of the products raised to their coefficients, Cl ion squared, right? That's what the K will equal to, the concentrations of our products raised to their coefficients. And if we're told that this number is 1.3 times 10 to the minus 12, we can solve for the concentration of lead ion when we put some lead chloride into water. So here's an example of what we're talking about. We have some water, and then I just put in some lead chloride. The lead chloride makes a big pile on the bottom because it's not soluble. However, there is a tiny amount that is soluble. And we are learning about how much lead chloride will actually be dissolved in a solution like this. Okay? And what we can do is we can think of the ice table for this sort of a reaction. Right? PbCl2 ionizing to the lead ion and 2 chloride ions. The initial concentration, this material we don't have to worry about. The initial concentrations of these we can say is 0 for this question, just wondering how much of this will dissolve. The change is going to be plus x and plus, we have the coefficient there, so 2x, and then the equilibrium concentration would be 0 plus x and 0 plus 2x. Right? So these are now my equilibrium concentrations. I take those equilibrium concentrations and put them up here, put them into our K value. So the equilibrium concentration of lead is represented by X here. That's the equilibrium concentration for lead. Equilibrium concentration from the chloride ion should be squared. That's 2x. So 2x squared. And the product of this should be my 1.3 times 10 to the minus 12. 2x squared is 2x times 2x, which is 4x squared times x, 4x cubed. Set that equal to 1.3 times 10 to the minus 12. I can use my calculator. 1.3 times, try again, 1.3 times 10 to the minus 12 divided by 4, getting rid of the 4 there, and then now I need to take the cube root. How do I take the cube root? I like to, there's a different way, but I'm not going to teach you that. You can look online if you want to, but I like to raise it to the 1/3 power. That's how you take the cube root cleanly in your calculator. 6.9 times 10 to the minus 5 is what x equals to. X equals 6.9 times 10 to the minus 5. All right. That is the molar solubility for our compound. That's our molar solubility. All right. It relates to the concentration. If I wanted to know the concentration of chloride ion, it's 2x's, so I can take this value, multiply it by 2. This is the concentration, this is the x, of lead ion at equilibrium. Okay? So, same thing. We're answering questions having to do with solids dissociating. Okay. We finished up last time answering this question right here. Will the following form a precipitate? And essentially what we're doing here is we're looking at our equilibrium reaction, looking at our equilibrium products, and asking, under the given concentrations of these products here, will I get a high enough concentration to drive the reaction back towards the product side? Okay? For the reaction to drive back towards the product side, the product of in this case, these two ions has to equal a value higher than that of our K for this reaction. Or in other words, the Q value, which is the quotient, the current equilibrium condition. And so we identified the concentration of calcium ion. Sarah, do you remember what we had to do to identify the concentration of calcium ion? What did we have to do?
Just 0.1 molar because we have.
Whoops, did we lose Sarah? Oh. So we took 20 milliliters of 0.1 molar. So that's what we started with, but then we added an additional 20 milliliters. So it takes the concentration of our 0.1 molar calcium ion in half. So this calcium ion concentration here ended up being 0.05. and the concentration of the oxalate ion, or the carboxylate ion here, was 20 mils, 0.01 of this ion, again divided by 2, so it was 0.005. We multiplied those values together, and then the result was, well, we'll just, because we did it on the last class, we won't do it now, but the result is 0.00025, or 2.5 times 10 to the minus 4. And because that is smaller than K, a precipitate won't form. Or sorry, it's larger. It's much larger. 2.5 times 10 to the minus 4 is larger than 2.3 times 10 to the minus 9, so a precipitate will form. All right, our Q, this value that we calculated, was larger than K, which means the reaction will drive to the left. We did the same thing for this reaction here and solved for a Q of 1.25 times 10 to the minus 8. And because that was smaller than our K, that means that the reaction will not drive to the left because these concentrations have not reached the threshold necessary to form a precipitate. Okay, so here's another question, just like those two, and we want to know, will a precipitate form? Lead nitrate is added to a solution of HCl until the mixture of lead is 0.1 molar and the mixture of chloride ion is 0.005 molar. Will lead chloride form? And we're given the KSP for lead chloride, 1.7 times 10 to the minus 5. Okay, then. What we need to do here is we need to identify the Q, the current Q for the formation of lead chloride. You want to help me with this one, Alyssa?
Sure. So I just wrote the equation to try to figure out what's happening. So I have the PbNO3 2 plus HCl forming PbCl2. Do we need to balance this equation?
Well, I don't think that it's necessary for this. No, I think you're right. We don't need to balance the equation. What is this KSP? What is this KSP for? I mean, it's a KSP, meaning it's a K for solubility product. So what is our insoluble material that will result? What did you say it was?
The PbCl2.
That's right. Very good. So that is our kind of our nuts and bolts equation, right? Will PbCl2 ionize into its products, right? And the K for this is 1.7 times 10 to the minus 5. Okay, now what do we do?
Then we can find the Q of the equation. And we would have to use the 1 molar of Pb. The other ones they gave like an amount, so do we just assume that it's a liter?
Well, in this one, they just said what?
It's added to a solution.
Yeah, until the mixture is 0.1 molar lead and 0.005 molar chloride ion. So that was nice of them.
Those two.
Yeah, it's a little bit simpler. They just actually give us the concentrations of the lead and the concentration of the chloride ion.
Okay, so just for 0.1 molar of the Pb plus 2, and then the 0.005 molar of the Cl minus, and that would equal 0.0005.
Okay, all right. Now, there's one more thing that we have to take into account here.
The Cl is squared, sorry.
That's right. It's squared. because the Q here is the concentration of the lead ion times the concentration of the chloride ion squared. Very good. So what do we get that time?
A lot of zeros. 0.00000025.
Times 2.5 times 10 to the minus, was that 6?
2, 3, 4, 5, 6. Yes, sir.
All right. So what does that tell us? Will it precipitate form?
Well, the Q is larger than the KSP, so it should form a precipitant.
All right. So how do we know that this Q is larger? 2.5 times 10 to the minus 6?
Oh, sorry. It's smaller.
It's smaller, isn't it? That's,
Because they're small.
yeah, that's an easy mistake to make. I always do that, right? Not paying close attention and just saying 6 is bigger than 5, right? But yeah. So hopefully we're right. We're predicting that no, a precipitate won't form. And we knew that because Q was actually smaller. Our current condition is smaller than our K. Therefore, more of this can build up before a precipitate will form. Okay, very good. This fact, the fact that you can precipitate out ions, for example, in this case, the lead ion, right? So in this problem over here, we did not precipitate out the lead ion because our concentration of chloride was only 0.005. But we could keep adding the chloride ion, and then eventually the lead ion would precipitate out. Now, if this was the silver ion here, then the SP, the KSP, would be a different value, right? So if we had a mixture of lead and silver, we would have two different KSPs, and we could find the chloride ion concentration that would make Q be right in the middle of those two KSPs, and we could effectively precipitate out one of the ions. So we call this selective fractionation or selective precipitation. So if, for example, like we just said, you'll find a concentration of your products in which neither will precipitate, and obviously there will be a concentration of your products in which both of the Q's will be greater than the KSP's. But because the two different ions will have different KSP's, there will also be a region where only one of your ions will precipitate. And this is that kind of a scenario. Well, we can identify that scenario. What concentration of iodide ion, is needed to precipitate one but not the other in a mixture of 0.1 molar lead and 0.1 molar silver ion? All right, so we need to get the KSP for both of these. So this is the KSP for silver ion. We identify if we have 0.1 molar silver ion. So let's do this on the paper here. If I have 0.1 molar silver ion, what concentration of iodide ion do I need to create a precipitation? Let's see, who can help me? Alyssa, can you help me with that one? Oh, no, sweet. That was Alyssa just went. Sarah's turn. Sarah, can you help me with that one? What concentration of iodide ion do I need to make my 0.1 molar silver ion precipitate? How would I find that?
Would you just substitute it in for the I, not KSP?
That's right. So the KSP of 8.3 times 10 to the minus 17, we could solve for what our I would have to be, right? Dividing by 0.1 here, so I would have to be the iodide ion concentration would have to be 8.3 times 10 to the minus 16. Alyssa?
Sorry, I have a question.
Yeah.
Would the KSP be provided?
Yeah, it would have to be provided for us, wouldn't it? We wouldn't be able to
Okay.
do this sort of thing. So 8.3 times 10 to the minus 16, that's the concentration of iodide ion necessary to precipitate out the silver. If we do this for the lead, what's the lead concentration or the iodide ion concentration necessary to precipitate out the lead? Can you tell there, Alyssa?
Well, the I has to be squared, so it would be 7.9 times 10 to the negative 10 square root of that.
Okay. So whatever the final iodine concentration is, squared, equal to 7.9 times 10 to the minus 9. So you took 7.9 times 10 to the minus 9 divided by 0.1. That is 7.9
Times 10 to the
negative 8. And then we have to take the square root of that, right?
Yes, sir.
And what did you say that value was?
Just a second. Sorry, I'm still doing it.
2.8 times 10 to the minus 4, is that what you said?
Sure.
Did I do that right or no? Well, let's see.
I just think I did it wrong.
Okay. So we got 2.8 times 10 to the minus 4. That's the molar concentration of iodide ion necessary to precipitate out the lead. So, Sarah, which is going to precipitate out first? If we gradually increase the iodine concentration, which is going to precipitate out first?
So would that be silver?
That's right. Because you only need 8.3 times 10 to the minus 16 molar iodide ion to precipitate out the silver. But you need 2.8 times 10 to the minus 4 to precipitate out the lead. So, any concentration above 8.3 times 10 to the minus 16 and below 2.8 times 10 to the minus 4 would precipitate out the silver and leave behind the lead. Okay? All right, so here's another type of question that asks essentially the same, it's the same type of thing, but instead of looking at iodide ion concentration, it's looking at hydrogen ion concentration or hydroxide ion concentration. So at what pH will one ion, the manganese or the iron, precipitate out, but not the other? Well, the way that hydroxide ion or the way that altering pHs precipitate out metals is by the presence of the hydroxide ion. Because, not that I needed to remind you, but Rule 5 here, all metal hydroxides are insoluble except for group 1. So therefore, metal hydroxides are insoluble. And identifying the concentration of hydroxide ion can be done simply by knowing the pH of the solution. Because we know that pH plus POH equals what, Alyssa? 14. That's right. So we have a pH meter, we know what the pH is, we know what the POH is, and from the POH we can identify the hydroxide ion concentration. Okay, so we have a chemical reaction of iron with hydroxide ion, or sorry, equilibrium expression where the solid iron hydroxide is dissociating. And then we look at the KSP for that and solve for the hydroxide ion concentration necessary to precipitate out the iron. Over here we solve for the hydroxide ion concentration necessary to precipitate out the manganese. Okay? Alyssa, can you tell me, you don't have to tell me right now, but can you work on identifying what the hydroxide ion concentration would be necessary to precipitate out? We have been provided the concentration of the metal here. All right, Alyssa, you're going to identify the concentration of hydroxide ion necessary to precipitate out the iron. And then Sarah, you're going to identify the hydroxide ion concentration necessary here to precipitate out the manganese. All right. After you get the hydroxide ion concentration, taking the negative log of that would be the POH, and then 14 minus the POH would be the pH. So that will give us the pH at which iron will precipitate out, this concentration of iron. It'll give us the pH at which manganese will precipitate out, and then we'll have a range of pHs in between in which we could precipitate out one, but not the other. Okay? So, I'll give you guys, what do you need? 48 seconds to do this one. So, go for it. The hydroxide ion concentration necessary to precipitate out the iron.
I got 1.6 times, or 1.16 times 10 to the negative 38. But I don't know if I think I did that right.
All right.
I'm not sure.
And then did you find the POH for that?
No, I haven't gotten there yet.
Okay. So, let's try that. 1.16 times 10 to the minus 38. And then I'm going to take the negative log of that value. Whoops. Negative log of that value. That doesn't seem right. Let's see where we're at. Oh, that's all it's going to give us then? Let's see what we did wrong. The hydroxide ion concentration. So the iron concentration was 0.1. And the hydroxide ion concentration, X cubed, equals 1.6 times 10 to the minus 39. So I take 1.6 times 10 to the... Oh, you didn't take the cube root of it, did you? Possibly, or did you?
I did, but I'm not sure.
Well, maybe you did. Let's see. So 1.6. Oh, yeah, maybe you did. Times 10 to the minus 39. That is... And then divided by 0.1. And then we raise that to the 1 over 3. Oh, there we go. 2.5 times 10 to the minus 13. 2.5 times 10 to the minus 13. So you might want to practice taking the cube root to make sure that you can get 2.5 times 10 to the minus 13 for this specific scenario. So the hydroxide ion concentration is 2.5 times 10 to the minus 13. And then negative log of that value, 12.59, is our POH. And then 14 minus that value should be our pH, 1.4. Whoops, 1.4. All right, Sarah, let's see. Did you have any luck with this one over here?
Yes. Do you want me to
Why don't we start off?
The pH.
Well, let's start off with the hydroxide ion concentration. Or do you have it
Okay,
still,
so-
or is it gone?
For that, I got 1.26 times 10 to the negative 6th.
10 to the minus 6, and then you took the negative log of that to get the pOH.
Yes, and that was 5.89.
All right, so your pH was
8.1.
8.1. Is that right? Okay, good. So then, any pH between 1.4 and 8.1 would precipitate out who first, Alyssa? Who would get precipitated out first, the iron or the manganese?
The manganese, because the KSP is larger.
So if I had a pH of 3, then I would precipitate out or I should say one closer to 8, so like, or pH of 8, not 8.1, but below 8.1, then I would precipitate out the manganese. Is that what you said, or the iron?
I thought it was manganese, but honestly, I have no clue. I'm confused.
Okay, so let's see here. Which has a higher concentration of hydroxide ion? The pH 8 or pH 1?
The pH 1.
pH 1? Isn't that acidic? Is that right? So if I have pH 1, 1.4, minus 14 minus the 1.4, that's 12.6 is my pOH. And then if I take 10 to the negative 12.6, right, that'll give me my hydroxide ion concentration. So at pH 1.4, my hydroxide concentration is 2.5 times 10 to the minus 13. Okay? At pH 8, I take 14 minus the 8.1. That gives me my pOH. I go 10 to the, 10 raised to the negative 5.9. That's my hydroxide ion concentration, 1.25 times 10 to the minus 6. All right. So to precipitate out the manganese, I need to have 1.25 times 10 to the minus 6. To precipitate out the iron, I need 2.5 times 10 to the minus 13. All right. So if I am at pH, let's say 0.5, the hydroxide ion concentration is too low to precipitate out anything. But as my pH increases, gets higher and higher, my hydroxide ion concentration is getting higher and higher. Right? So therefore, if I get above pH 1.4, my hydroxide ion concentration is enough that the iron will begin to precipitate out. But I still don't have enough to precipitate out the manganese. So as I get closer to pH 5, 6, 7, 8, and then as soon as I get to 8.1, I have enough hydroxide ion concentration to precipitate out the manganese. So the iron will go first and then the manganese. All right, very good. Should we try one more, or do you guys feel like we got it already?
I would say we should try one more.
All right, let's do it then. When a solution containing 0.1 molar of calcium or 0.1 molar of magnesium, what concentration of carbonate will precipitate one but not the other? All right. Let's go for it. Do you want to talk me through it, Alyssa?
Sure. I'm just writing out the equation that we're going to find. So,
Mm-hmm.
it'll be CO3 minus 2. Yeah, CaCP. And then it goes to Ca plus 2 and CO3 minus 2. And then do you want to do the other equation now?
Sure.
Just do that first? And then we have the MgCO3, and that goes to Mg minus plus 2, and then CO3 minus 2.
All right.
And then so we know the concentration of the Ca, and which is 1 molar, and then we know the KSP, so we can do 4.8 times 10 to the negative 9 equals 0.1, which represents the concentration of the Ca plus 2 times X, which symbolizes the concentration of CO2. And then we can solve that, which is 4.8 times 10 to the negative 9, or to the negative 8, sorry. And then the other equation, it is the concentration of the Ca or CO2 is 4.0 times 10 to the negative 3, because that's 0.01 molar.
Okay, so for this one here, we had 4.0 times 10, 4.0 times 10 to the minus 5. And that's equal to the magnesium ion concentration, 0.01 times an unknown concentration of carbonate. Okay, and you said that X is equal to 4.0 times 10 to the minus 3. Therefore, which one of these will precipitate out one but not the other? Do we have any? We're at 3 and the minus 8.
So it would have to be in between 3 and 8, so 2 of them are in between.
Let's see, is 5 times 10 to the minus 8? Is that high enough? What's that?
Isn't that greater than both of them?
So then that would mean it would precipitate out. Oh, no. Okay, so 5 times 10 to the minus 8 is more than the 4.8 times 10 to the minus 8, is it? But not greater than 4 times 10 to the minus 3, right?
Yes.
Okay, so A would precipitate out one, but not the other. How about 5 times 10 to the minus 7?
It would precipitate out the calcium but not the magnesium as well.
Okay. And then 5 times 10 to the minus 6?
The same.
Whew. So we got all of these will do. Did we make a mistake here? Oh, good. We got it. Excellent. All of these will do because they're between 4.8 times 10 to the minus 8 and 4 times 10 to the minus 3. Now, which one will precipitate out and which one will not? Sarah? At these concentrations?
I'm sorry, my microphone just went weird. What did you say?
which one will precipitate out. So we decided that all of these concentrations will precipitate out one, but not the other. And we want to know which one will precipitate out.
Okay, so all of them will precipitate out the CaCO3.
That's right, the calcium ion, and leave behind the magnesium. Okay, very good. One more, or do you think we call it quits? What do you think, Alyssa?
I felt a lot better on that one, but this one has the pH, so it might be good to do this one too.
All right, what do you think, Sarah? Or, well, Alyssa says it's good enough. Let's do it. All right. So, Sarah, you're going to help me with this one then. How would you set this one up?
So all right, so would we make the first equation HCU?
Well, what is it about the pH that would precipitate out copper or lead? Do you remember from that other slide?
Oh, was it the hydroxide?
That's right. So we're looking at precipitating out copper 2, so it's going to be CuOH with 2 there. And its equilibrium, its dissociation, would be a copper ion and 2 hydroxide ions. All right. It's supposed to be a 1 there. What would the other equation look like?
So that would be PbOH2.
All right. Lead ions and 2 hydroxide ions. Okay. So we have a KSP here for, oh, actually, you know what? Yeah. Well, we'll finish this one using 1.6 times 10 to the minus 16 for the copper, 6 times 10 to the minus 16 for the copper, and then 3 times 10 to the minus 7. 3 times 10 to the minus 7 for the lead hydroxide. Okay. So how do we, what were our concentrations? Was it 0.1 molar each? Yeah, 0.1 molar. So what do we do from now? For now, Sarah, what's next?
Okay, so we can say that 6 times 10 to the negative 16 equals 0.1. Yeah, 0.1 times concentration of OH squared, or just X squared.
Okay.
So
Solve for X there. Six times 10 to the negative 16 divided by 0.1, and then we take the square root of that value. 7.7 times 10 to the minus 8. Is that what you got, Sarah?
yes.
Okay. Then this one down here.
Yeah, that'll be 3 times 10 to the negative 7th equals 0.1 times X squared.
And just in case anybody's wondering, that 0.1 comes from these initial concentrations here. Those initial concentrations. 0.1 X squared. All right, so 3 times 10 to the minus 7 divided by 0.1. Oh, try again. 3 times 10 to the minus 7 divided by 0.1. And then I'm going to take the square root of that. So 1.7 times 10 to the minus 3. All right, what do I do now, Sarah? Or do I have the answer or not quite?
All right, so those are both the concentration of OH. So if you take the negative log of that answer, you should get the POH.
Okay, so you're saying the POH is 2.76.
Yeah, and then if you just subtract that from 14, you'll get the pH.
11.24. All right, and then we got 7.7 times 10 to the minus 8 up here. The negative log of that value would be the POH. 14 minus that value, so a pH of 6.88. 6.89. Okay, so if I had a solution that had a pH of 9, which would precipitate out? What do you think, Sarah? pH 9.
I think the CuOH.
That's right. Because at pH 9, we have more hydroxide ion than at pH 6.89. And the more hydroxide ion is going to cause this reaction to shift to the left. Very good. So pH in between these two would selectively precipitate out the copper over the lead. pH 5 wouldn't precipitate out anything. pH, where are we at? 12 would precipitate out both of them. Okay, very good. Any questions on that one?